You ever look at one of those massive industrial plants, with thousands of moving parts, and just wonder, how do they manage to make a perfect product every single time? Well, it's not magic. It's a field of engineering that's pretty much all about predicting the future. Let's take a look at how it works. So picture this. Our story kicks off at 3 in the afternoon, right after a shift change. We've got a new operator who's just trying to get the hang of things, and, well, they misread the flow meters for two streams that are feeding into a big mixing tank. It's a small error, really, an easy one to make. Now, on the surface, this mistake looks simple enough. The total flow rate into the system is still 30 liters per minute, right? The operator just swapped the values for stream 1 and stream 2. It seems pretty minor, but trust me, the consequences of this are going to ripple through the entire process. So, the big question for the engineers is, what happens now? How is this tiny little change going to affect the final product that comes out of the system? To figure that out, they basically have to see the future. And how do they do that? They build a model. This is always the first step in any kind of process investigation. You have to understand exactly how the system behaves when things change. The whole field we're talking about here is called process dynamics. It's not about the steady, normal, predictable state of the plant. Nope. It's about what happens in those moments after something goes wrong, or any change is made, really. You could call it the science of the in-between. Okay, so let's look at the first domino to fall. Because those flow rates got swapped, the concentration of the chemical mixture going into the next stage, which happens to be a heater, immediately drops. It goes from a steady 3 grams per liter all the way down to 2. And this change, right at the inlet, is instantaneous. But, and this is the crucial part, the concentration at the outlet of the heater doesn't just snap to that new value. The tank has volume, right? It's got a sort of memory of what used to be in it. So what happens is the concentration starts to decrease along this perfect, predictable exponential curve. It's changing, yeah, but it's not chaotic at all. And it's not just about the chemical concentration. The same exact thing happens with energy. The operator's mistake also made the inlet temperature drop from 45 down to 35 degrees Celsius. So if the heater just keeps pumping in the same amount of energy, the outlet temperature is also going to start a slow, predictable decline toward a new, lower, steady temperature. So we have these nice, predictable curves. But how do engineers describe them with any kind of precision? Well, they use a special language for it, a mathematical one that lets them capture the very essence of this change. You see that predictable curve we were just looking at? It can be described perfectly by something called a differential equation. Now, I know what you might be thinking, but don't let the name scare you. Really, try to think of it less like some crazy complex math problem and more like a sentence that's just written in the native language of the physical world. This equation right here is the key. It's basically a sentence that says the rate at which the concentration is changing, that's the dC over dt part, is directly related to the concentration flowing in versus what's already in the tank. If we can solve this thing, we can predict the concentration at any moment. We can literally see the future of our product. But let's be honest, solving differential equations can be a little tricky. So engineers have a secret weapon. It's a very clever mathematical tool that makes the whole thing incredibly elegant and way, way simpler. It's called the Laplace transform, and the genius of it is that it doesn't solve the hard problem directly. What it does instead is it transforms the problem into a totally different mathematical world, a world where the solution is actually easy, and then it just transforms that easy solution back. Think about it like this. You've got this really difficult text written in a tough language. Let's call it calculus land. So you use a translator, that's our Laplace transform, to convert it into a much simpler language, algebra land. You read it, you understand it, and then you use an inverse translator to bring the meaning back to your original language. It's just a brilliant workaround. So here's the magic trick. The hardest part of our differential equation, that d over dt term, in algebra land, it just becomes simple multiplication. That's it. It turns calculus into algebra. And once you solve the algebra, you just transform back to get your prediction of how the concentration changes over time. Okay, so we've seen that engineers can accurately predict how a system is going to fail. They can literally see the future of the product's quality. But, prediction is only half the battle. The real goal here is control. I mean, what's the point of knowing disaster is coming if you can't do anything to stop it? How do we take this amazing predictive power and use it to build a system that can fix problems all on its own, maybe even before they become actual problems? The answer is a feedback loop. It's pretty cool how it works. You install a measurement device, like a temperature sensor, that's just constantly watching the process. This information gets fed back to a controller, which is kind of like the brain of the operation. The controller compares the actual temperature to the temperature you want it to be. That's the set point. And if there's a difference, it sends a signal to a final control element, maybe a valve, telling it to make an adjustment. The whole point of this loop is to handle disturbances, like our operator's 3 p.m. mistake, automatically. It's constantly measuring, comparing, and correcting, making sure the product stays perfect and the process stays safe, without a human having to watch it every single second. And this really brings us to our final thought. With this kind of system in place, could a smart controller have noticed that drop in temperature and automatically cranked up the heat, fixing the operator's mistake before the shift supervisor even knew something was wrong? Well, that right there, that's the power and the promise of process control.